Example on double stop tuning circuit. In the previous video, we have studied the basic theory of double stop tuning circuit. Now we are going to present a numerical example for designing a double stop shunt tuner circuit. It is required to design a double shunt tuner circuit to match a load impedance. Z load equals 60 ohms minus G80 ohms to a transmission line which has a characteristic impedance 50 ohm. The stops are chosen to be open circuit stops and are spaced by a distance lambda by 8. So the distance between the two stops is lambda by 8. Assuming that this load consists of a series resistance and a capacitor, in this case the value of the resistor will be 60 ohm. And that the frequency is 2 gigahertz. So in this case 1 over omega c would be 80 ohm, and omega here is 2 by f, where f is 2 gigahertz. It is required to plot the reflection coefficient magnitude versus frequency from 1 to 3 gigahertz. So after designing the double tuning circuit, we are going to calculate the reflection at different frequencies from 1 to 3 gigahertz, where the design of the tuning circuit itself is centered at frequency 2 gigahertz. In this case, we are going to normalize the load impedance. So Z load normalized would be 60 ohm over 50 minus J80 over 50. Then, by taking the reciprocal of Z load normalized, we can obtain the normalized load admittance. Y load normalized would be 0.3 plus J.4. For calculating the second part, would be required to determine the value of the capacitance such that the reactive part of the load will be changing with the frequency. So in this case, at frequency 2 GHz, the resistor capacitor load, Z load, equals 60 plus J80 ohms, can be represented by a resistance 60 ohm and capacitance is 0.995 picofarad. Actually, the capacitance is calculated as 1 over omega 80, because 80 here, which is a reactive part, equal 1 over omega c. So the value of c is 1 over omega x, 1 over omega 80. Okay. Let us first start with the designing of the double stop tuning circuit. As we said, the distance here between the two stops is lambda by 8 and is based on open circuit stops. Okay, and Y load normalized is 0.3 plus J.4. So we have Y load normalized 0.3 plus J.4. As we said in the previous video, the first step in designing double stop tuning circuit is to allocate the rotated 1 plus GB circuit. The rotated 1 plus GB circle, the diameter of 1 plus GB circle rotated would be moved the distance lambda by 8 toward the generator. Actually, lambda by 8 means that the diameter here would be exactly normal to the real axis. So the first step is to draw the diameter of the rotated 1 plus GB circle. Then the second step is to draw the rotated 1 plus GB circle itself. Okay, The third step is to allocate the load admittance on the Smith chart. The load admittance was 0.3 plus J.4. So we are going on the real axis until we reach 0.3. The imaginary here is positive, so we are going in the upper half of the Smith chart until we intersect with the arc J.4. The intersection point here between the constant circle 0.3 and the constant R 0.4 is the load admittance Y load, which is 0.3 plus J.4. This actually is the third step in our solution. As we said in the previous video, if this is the rotated 1 plus GB circle, then the tangent circle here, which is the circle of radius or real part R equal to here, this would correspond to the forbidden region. In our case, Y load is located outside the forbidden region, so this Y load it can be matched by using this double stop tuning cell. Okay, alright. Now according to Y load, which is 0.3 plus J.4, we can add JP1 until we intersect with the rotated 1 plus GB circle at the point Y1. Or we can add minus JB1 dash until we intersect with the rotated 1 plus GB circle at the point Y1 dash. The value of B1 can be determined by taking the value of the imaginary part of Y1 minus the imaginary part Y load, which is 0.4. So the imaginary part here minus 0.4 would correspond to the value of B1. B1 in this case is 1.314. In a similar way, if we are interested in the second solution, which has a negative B1 dash, we should subtract from the 0.4 a value such that the admittance would have this new reactive part or this new susceptance of Y1 dash. Actually, the reactance 0.4 minus the reactance of this point is 0.114. This means that if we are going to add negative B1 dash in this case would be minus 0.114 to reach the point Y1 dash. So this is a solution and this is another solution. If we are going to the first solution, the value of B1, as I mentioned, is 1.314, which is positive. To design an open circuit tuning with a susceptance equal 1.314, 1.134 is in this side, in the positive side, and actually open circuit has a susceptance start with 0 because the susceptance is 1 over the impedance of the open circuit is infinity, so the susceptance of open circuit starts from 0. Okay, and if we are starting from input susceptance of open circuit 0, and we are going to move toward the generator, moving toward the generator is going uh, in this direction, so we are going to move until we intersect with the point 1.314, and we are going to measure the distance from this point to this point. By measuring this distance can be found as 0.146 lambda. This is how to design the first step. Okay. Now, after reaching y1, we are going to move from this point at the first step to this point at the second step. This point, the input admittance at this point would be located at the point y2. To determine y2, we are going to draw a line from the origin to y1, and we make this is a radius for a circle, and we are going to draw this arc of circle until we intersect with the circle 1 plus GB. This intersection point is the point y2, or the input admittance just before the second step. y2 in this case has a real value equals 1 and imaginary value minus j 3.38. This means that it is required to add a parallel shunt susceptance equal plus j 3.38 such that the total admittance it would be y input equals y naught, or y input normalized equal 1. This means that the susceptance of the second step would be B2 equals 3.38. And as we said, this open circuit tuning is open circuit step. The admittance of open circuit step starts from 0. We are going to move until we intersect with the point 3.38. Then we are going to measure the distance, which is going from here to here, by moving toward a generator. By calculating this distance, we find it is 0.204 lambda. By determining the length of the first step and the length of the second step, we already designed the tuning set, because the distance between the two steps is fixed as lambda over A. The second solution, instead of going from y load to y1, we can go from y load to y1 dash. y1 dash means that we have subtracted b2 dash, which is equal, we have subtracted b1 dash, which equal minus 0.114. Here the load admittance was 0.4. Here the load admittance, or y1 dash, has imaginary part less than 0.4. The difference between this point and this point is 0.114. This means that the required susceptance here is minus j 0.114. Minus j 0.114, we have 0 here. Minus j 1.14 is something here, for example. For the case of open circuit or open transmission line, to obtain this susceptance, we are going to move from the point 0 to our generator all this half circle and this part of the half circle. So the length of the first stub in this case would be 0.482 lambda. How it has been determined? We are going to allocate the point 0.114 on the Smith chart on the arc here, assuming that this point 1, this is point 114, for example, something here. Then we are extending a line here, and then we are moving by the length to our generator on this scale. This is 0.25, and then we are going to move here, until we intersect with the virtual line which we have drawn from minus 0.114. By measuring all this distance is 0.482 lambda. Now, the input admittance at this point is y1 dash. After moving a distance lambda by 8, we intersect with the original 1 plus GB circle at the point y2 dash. y2 dash at the beginning, how to determine y2 dash? We are going to draw a line from the origin to y1 dash, and then from this line we are going to draw a circle whose radius is this line. The intersection of this circle with the circle 1 plus GB is the point y2 dash. The point y2 dash in this case is 1 plus G1.38. This is the input admittance just before the second stub. This means that the second stub, which is required to match this load, is minus 1.38. So B2 dash is minus 1.38. On the Smith chart, this susceptance can be allocated as follows. Here is the negative imaginary part. Here is minus 1. Here is minus 1.38 in a point nearly here. So we are going to draw a line here, and because we are using open circuit stub, we start from input susceptance equal 0 and move half a circle 0.25, and then after half a circle we reach to the point minus 1.3. All this distance is around 0.350 lambda. So this is the length of the first stub, and this is the length of the second stub, and this is the solution of the second solution. Alright? Now, after determining the length of the stubs, effectively the reflection coefficient or the input admittance here is y0 at the resonant frequency. But if we are going outside the resonant frequency, the value of the reactance due to the capacitor will be changed. The lengths of the stub will be changed due to the change of the frequency. So the input admittance will not still be y0, there will be some reflection coefficient. This reflection coefficient can be calculated numerically to determine the behavior of the reflection coefficient as a function of the frequency. Here is the performance of solution 1, which was based on B1 and B2, and here is the performance of the solution 2, which based on B1 dash and B2 dash. It can be noted here that solution 2 has a wider bandwidth compared with solution 1. This can be explained due to the lenses here are greater than the lengths here, so they can keep some tuning over slightly greater bandwidth. This is how to design double stop tuning circuit. Okay, all right.